We are taught that the universe is a crowded place, a tapestry woven thick with galaxies, stars, and nebulae. But this is a deception of perspective, a byproduct of our position within a dense galactic suburb that obscures the true, staggering reality of the cosmic architecture. When we look up at the night sky, our eyes are naturally drawn to the pinpricks of light, the luminous debris of a much larger and more mysterious process. Yet the vast majority of the volume of the observable universe contains no stars, no planets, and no light at all, existing instead as a series of colossal, empty chambers known as cosmic voids. These voids are not merely accidental gaps in the distribution of matter, but are essential components of the large-scale structure of the cosmos, acting as the negative space that defines the luminous filaments of the cosmic web. To understand the scale of this emptiness, we must first look at the universe through the lens of the cosmic web, a complex and shimmering network of dark matter filaments and gas that spans the entirety of existence, acting as the scaffolding upon which all visible matter is hung. This web resembles a neural network or a vast three-dimensional sponge, where the filaments represent the dense regions where gravity has pulled matter together to form galaxy clusters, and the holes in the sponge represent the voids, regions where the density of matter is so low that the expansion of space itself has pushed the remaining atoms outward toward the edges. The most famous and perhaps the most mysterious of these regions is the Boötes Void, often referred to as the Great Nothing, a spherical expanse of space so vast and so empty that it challenges our fundamental understanding of how the universe organized itself after the Big Bang.
Discovered in 1981 by astronomer Robert Kirshner and his team during a routine redshift survey, the void was initially thought to be an error in the data, a statistical fluke that would disappear with more precise measurements. But as the survey continued, the reality of the situation became clear. They had found a hole in the universe. In a volume of space that should, by all standard cosmological models, contain at least 2,000 galaxies, they found only a handful, creating a discrepancy that forced physicists to reconsider the role of gravity and dark energy in the formation of large-scale structures. This region, located in the vicinity of the constellation Boötes, is approximately 330 million light-years in diameter, a distance so immense that if the Milky Way were positioned at its center, we would not have known that other galaxies existed until the advent of high-powered telescopic technology in the mid-20th century. To visualize this scale, imagine traveling at the speed of light, crossing the entire diameter of our own galaxy in 100,000 years, which is already a time frame that dwarfs human history. Yet to cross the Boötes Void, you would need to maintain that impossible speed for over 300 million years. During this journey, you would encounter almost nothing: no stars to guide your way, no nebulae to illuminate the darkness, and no planetary systems to offer a sense of scale, creating a sensory deprivation on a universal level that highlights the sheer dominance of the vacuum. This emptiness is not a defect or a tear in the fabric of reality, but is instead the result of billions of years of gravitational evolution, where the slight initial density fluctuations in the early universe were amplified by the relentless pull of gravity, drawing matter away from the underdense regions and concentrating it into the walls and filaments that surround the void.
This process, known as the hierarchical formation of structure, suggests that the universe is undergoing a continuous process of refinement where the rich get richer and the poor get poorer, as galaxy clusters grow larger by stripping the surrounding voids of their remaining gas and dust. As we delve deeper into the architecture of the cosmic web, we find that the voids themselves are not entirely empty, but instead contain a thin, ethereal population of what astronomers call void galaxies, lonely island universes that have evolved in total isolation. These galaxies, such as the spiral galaxy NGC plus 01-02-015, are some of the most pristine objects in the cosmos, having never experienced the violent collisions or tidal disruptions that are common in dense galactic clusters, meaning that their chemical composition and structural integrity remain largely unchanged since the dawn of time. Studying these hermit galaxies provides us with a unique window into the past, allowing us to see how a galaxy develops when it is left entirely to its own devices, unbothered by the gravitational influence of neighbors or the turbulent flows of intergalactic gas. The existence of these galaxies within the Boötes Void is a testament to the resilience of matter, illustrating that even in the most desolate regions of the universe, the laws of physics still conspire to create structure, albeit at a much slower and more solitary pace. The formation of the Boötes Void is often explained through the theory of bubble nucleation, or the merging of smaller voids, a process where multiple low-density pockets in the early universe expanded until they touched, eventually merging into a single gargantuan supervoid.
This theory is supported by the fact that the Boötes Void is not a perfect sphere, but has a slightly irregular, multi-lobed shape, suggesting that it is the product of several smaller voids that have coalesced over eons, much like bubbles in a kitchen sink, merging to form a larger pocket of air. This merging process is driven by the expansion of the universe, which acts as an outward pressure that stretches the voids, while gravity acts as a counteracting force that pulls matter toward the filaments, creating a cosmic tug-of-war that shapes the very geometry of space-time. The result is a universe where the vast majority of the volume is occupied by these silent, dark cathedrals, while the light and life we are familiar with are relegated to the thin, fragile walls that separate them. In the context of the cosmic microwave background, the afterglow of the Big Bang, we can see the seeds of these voids in the tiny temperature fluctuations that existed when the universe was only 380,000 years old, where the slightly cooler spots represent the regions that would eventually become the voids. These fluctuations, caused by baryon acoustic oscillations in the primordial plasma, set the stage for everything we see today, dictating the placement of every galaxy cluster and every void with mathematical precision. The fact that we can trace the origin of a structure as massive as the Boötes Void back to the first moments of creation is a triumph of modern cosmology, providing a sense of continuity and order in a universe that often seems chaotic and indifferent. It suggests that the emptiness is not a lack of purpose, but a fundamental part of the design, a necessary component of a system that requires balance between the dense and the diffuse.
When we consider the physics of the vacuum within the void, we encounter the concept of dark energy, the mysterious force that is causing the expansion of the universe to accelerate, and which is thought to be most dominant in the empty regions of space. In the dense environment of a galaxy cluster, gravity is strong enough to counteract the effects of dark energy, keeping the galaxies bound together. But in the vast reaches of the Boötes Void, dark energy reigns supreme,
pushing the boundaries of the void outward at an ever-increasing rate. This means that the voids are not just static, empty spaces, but are dynamic, growing regions that are actively pushing the rest of the universe away, acting as the primary drivers of cosmic expansion. Some theoretical models even suggest that the voids could be viewed as repellers, regions that exert a net outward force on the surrounding matter, a concept that has led to the discovery of the dipole repeller, a massive void that is currently pushing the Milky Way and the rest of the local group toward the Shapley supercluster. This realization shifts our perspective of the void from a passive vacuum to an active participant in the evolution of the cosmos, a force that shapes the movement of galaxies across millions of light years. It is a reminder that in physics, the absence of matter does not equate to the absence of influence, and that the geometry of space itself carries energy and momentum that can dictate the fate of entire civilizations. The Boötes Void, in its silent majesty, serves as a laboratory for the study of the fundamental constants of nature, providing an environment where the noise of baryonic matter is stripped away, leaving only the pure underlying laws of gravity and quantum mechanics. It is here, in the heart of the Great Nothing, that we might one day find the answers to the most profound questions about the nature of dark matter and the ultimate destiny of the universe.
As we move through this chapter, we must also consider the psychological impact of such vastness, the way the human mind struggles to comprehend a distance of 330 million light years, or a volume of space that could contain billions of suns without a single one being present. This is the essence of competence porn in the cosmic sense. The ability to look into the abyss and describe it not with fear, but with clinical, academic precision, using the language of mathematics and physics to bridge the gap between the known and the unknowable. We use terms like isostatic equilibrium and hydrodynamic instabilities to describe the behavior of gas at the edges of the void, and we calculate the geodesic incompleteness of spacetime near its boundaries, all in an effort to tame the infinite with the tools of the finite. This intellectual mastery provides a sense of safety, a feeling that if we can name the void and measure its dimensions, we are no longer lost within it, but are instead observers of a grand, orderly process. The ocean wave of our narrative now pulls us toward the realization that the Boötes Void is just one of many such structures, a single cell in a much larger cosmic organism that continues to grow and change. There are even larger voids, such as the Eridanus supervoid, which is associated with a mysterious cold spot in the cosmic microwave background and may span over 1 billion light years, suggesting that the scale of emptiness in the universe is even greater than we once imagined. These supervoids represent the final frontier of observational astronomy, regions so large and so faint that they require our most advanced satellites and algorithms to map, yet they hold the key to understanding the total mass-energy equivalence of the universe. By measuring the way light from distant quasars is bent and stretched as it passes through these voids, a process known as weak gravitational lensing, we can map the distribution of dark matter that we cannot see, revealing the invisible skeleton of the cosmos. In the quietude of this exploration, we find a strange comfort in the fact that the universe is mostly empty, as it implies a level of stability and permanence that a more crowded universe might lack. In a universe packed with matter, the frequency of cataclysmic collisions and gravitational disruptions would be so high that the long-term evolution of life might be impossible.
but the presence of the voids provides the necessary buffer zones, the vast distances that keep the fires of the stars at a safe and manageable distance. The voids are the insulation of the cosmos, the dark, cool layers that protect the fragile structures of the filaments from the overwhelming energy of the Big Bang's aftermath. They are the silence between the notes of a symphony, the essential pauses that allow the melody of the galaxies to be heard. As we conclude this initial descent into the architecture of the cosmic web, we are left with a picture of a universe that is both intricately connected and profoundly isolated, a paradox of structure and void that defines the very nature of existence. We have seen how the Boötes Void was formed from the smallest quantum seeds, how it grew through the merging of lesser voids, and how it now stands as a monument to the power of expansion and the persistence of the vacuum. We have met the lonely galaxies that call this abyss home, and we have contemplated the dark energy that drives the void's relentless growth, all while maintaining the clinical detachment of the cosmic guide.
The journey into the great nothing has only just begun, and as we move forward, we will continue to peel back the layers of this celestial mystery, moving from the macroscopic scale of superclusters to the microscopic scale of the particles that drift within the dark. The transition from the crowded filaments of our local neighborhood to the heart of the Boötes Void is not a journey of distance alone, but a journey of the mind, a recalibration of what we consider to be important or even real. In the void, the traditional markers of astronomical significance, supernovae, black holes, and pulsar timing give way to more subtle phenomena, such as the integrated Sachs-Wolf effect, where the gravitational potential of the void itself alters the energy of passing photons. This effect causes light to lose energy as it enters the void and fail to regain it as it exits, due to the accelerated expansion of space during the photon's transit, resulting in a slight cooling of the light that we can detect as a cold spot on our maps. This is the safe tension of our narrative, a catastrophic loss of energy on a galactic scale described with the calm of a laboratory report, a phenomenon that tells us more about the shape of the universe than 1,000 exploding stars. We must also reflect on the lullaby lattice of the universe's construction, where every atom in your body was once forged in the heart of a star that was itself part of a filament that defined the boundary of a void. This connection means that you are not an observer of the cosmic web, but a part of it, a microscopic node in a network that spans billions of light years, and your very existence is a byproduct of the same gravitational instabilities that created the Boötes Void.
This realization is the ultimate zoom out, a shift in scale that reminds us of our place in the grand design, without inducing the vertigo of insignificance, but instead offering the warmth of belonging to a system that is both vast and meticulously ordered. The void is not a place to be feared, but a place to be understood, a reflection of the same physical laws that govern the fall of an apple or the orbit of the moon, scaled up to the limits of the observable horizon. As the light of our understanding continues to illuminate the dark corners of the Boötes Void, we find that the competence porn of our exploration lies in our ability to predict the behavior of these structures over billions of years. we can simulate the future of the cosmic web using supercomputers, watching as the voids grow larger and the filaments grow thinner until the universe becomes a series of isolated island universes separated by an infinite and uncrossable sea of empty space. This future, while seemingly lonely, is described by physicists with a sense of profound beauty, a state of maximum entropy where the complexities of the universe are finally smoothed out into a perfect, everlasting stillness. It is the ultimate resolution of the intellectual knot, the answer to the question of where it all ends, delivered with the clinical detachment of a professor explaining a well-understood chemical reaction. In the coming chapters, we will explore the specific galaxies that inhabit the void in greater detail, examining their strange, unhindered evolution and the unique challenges they face in a region where the nearest neighbor is millions of light years away. We will look at the chemistry of the intergalactic medium within the void, a substance so thin that it contains only a few atoms per cubic meter, yet which holds the record of the universe's thermal history.
And we will contemplate the possibility of even larger structures, the hypervoids, that may exist beyond the reach of our current surveys, waiting to be discovered by the next generation of cosmic explorers. But for now, let the scale of the Boötes Void sink in. Let the image of the great nothing fill your mind with its silent, dark, and perfectly safe expanse, as we drift further away from the light of the stars and into the heart of the cosmic sanctuary. The silence here is absolute, a vacuum so perfect that it would baffle any terrestrial engineer. Yet it is a silence that speaks volumes about the history of our world. Every cubic centimeter of this void has been touched by the expansion of the universe. Every part of its volume has been shaped by the invisible hand of dark energy, and every photon that passes through it carries a message from the beginning of time. We are merely the translators of these messages, the guides who walk the line between the light and the dark, finding the meaning in the emptiness and the structure in the void. As we move into the next phase of our journey, keep this image of the cosmic web in your mind, the shimmering filaments and the dark hollow spaces, and remember that you are safe within this architecture, a part of the grand hypnotic rhythm of the universe. The Boötes Void is not a hole in the universe, it is a part of its breath, a slow exhalation that has lasted for 13 billion years. It is the space where the universe thinks, where the laws of physics are allowed to play out without the interference of too much matter, and where the ultimate fate of the cosmos is being written in the language of the vacuum. By studying it, we are studying ourselves, for we are the product of the same forces that created the void, the same gravity that pulled the stars together, and the same expansion that pushed the voids apart.
In the end, there is no nothing, only different states of something, and the Boötes Void is perhaps the most pure something we have ever found. It is the canvas of the cosmos, the background upon which all the drama of existence is painted, and without it, the stars would have no place to shine. So we continue our drift, deeper into the academic mystery of the great nothing, guided by the principles of clinical observation and the safe tension of scientific discovery. The path ahead is dark, but it is a darkness we have mapped, a darkness we understand, and a darkness that welcomes us with the cold, silent embrace of the infinite. There are no surprises here, only the steady, predictable application of the laws of thermodynamics and the graceful expansion of the Friedmann-Lemaitre-Robertson-Walker metric, a mathematical certainty that provides a foundation for our sleep and a structure for our dreams. The void is waiting, and we are ready to enter. To understand the profound silence of the Boötes Void, we must first transport our consciousness back to the year 1981, a period when our maps of the cosmos were largely two-dimensional, and our understanding of the large-scale structure of the universe was governed by the assumption of perfect uniformity. At this time, astronomers viewed the heavens as a relatively smooth distribution of matter, believing that if one were to zoom out far enough, the galaxies would appear as a fine, even mist, much like the droplets of water in a morning fog that obscure the landscape without forming any significant gaps or clusters. This concept, known as the cosmological principle, suggested that the universe was both homogeneous and isotropic, meaning that it looked the same from every vantage point and in every direction, providing a comforting sense of order and predictability to the burgeoning field of physical cosmology.
However, a small team of researchers, led by Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman, was about to introduce a complication into this serene model, a discovery that would emerge not from a sudden flash of light, but from the clinical and methodical accumulation of absence. They were conducting a redshift survey of the northern sky, specifically targeting the region within the constellation of Boötes, with the intention of measuring the three-dimensional positions of galaxies to create a more comprehensive map of our cosmic neighborhood. Using the 1.5-meter Tillinghast telescope at the Fred Lawrence Whipple Observatory, they meticulously gathered the faint, ancient photons that had traveled for hundreds of millions of years to reach the silicon sensors of their instruments, converting this light into data that could reveal the hidden architecture of the vacuum. The process of a redshift survey is one of clinical patience, requiring the observer to sit in the quiet, climate-controlled hum of the observatory while the telescope tracks the rotation of the Earth with mathematical precision. To determine the distance of a galaxy, astronomers must perform spectroscopy, a technique that involves passing the collected light through a prism or a diffraction grating to reveal its constituent colors and the specific absorption lines that act as chemical fingerprints. Because the universe is expanding, the space between us and distant galaxies is constantly stretching, which causes the wavelengths of the light traveling through that space to stretch as well, a phenomenon known as cosmological redshift. By measuring the degree to which these spectral lines have shifted toward the red end of the spectrum, researchers can calculate the velocity at which a galaxy is receding, which, according to Hubble's law, provides a direct and reliable measurement of its distance from Earth. In 1981, this technology was reaching a level of maturity that allowed for the mapping of thousands of galaxies. Yet, as the data from the Boötes region began to populate their charts, the researchers noticed a peculiar and unsettling trend in the distribution of their findings. Instead of finding a continuous and even spread of galaxies across the volume they were surveying, they encountered a massive, inexplicable gap where the expected signals of galactic life simply ceased to exist. This gap was not a small pocket of emptiness, but a staggering expanse of nothingness that seemed to defy the statistical probabilities of the time, suggesting that a significant portion of the universe was far emptier than anyone had previously dared to imagine. As the data points were plotted in three-dimensional space, they formed a clear and distinct boundary,
revealing a spherical region approximately 250 to 330 million light-years in diameter that contained almost no detectable matter. To put this into perspective, a region of this size should have contained at least 2,000 galaxies based on the average density of the observable universe. Yet the 1981 survey found only a haunting, absolute silence. The initial reaction within the scientific community was one of rigorous skepticism, as is common when a long-held paradigm is challenged by a null result, leading many to suspect that there might be an error in the survey's sensitivity or a failure in the sampling methodology. The researchers themselves were forced to consider the possibility of instrumental bias, perhaps a hidden defect in the spectrograph, or a systematic miscalculation of the redshift values that had somehow created an artificial void in their data. They returned to their instruments, recalibrating the sensors and verifying the coordinates, but the hole in the universe remained, a persistent and safe mystery that demanded a new way of thinking about the evolution of cosmic structure.
The discovery of the Boötes Void introduced what we might call an intellectual knot, a safe problem that allowed physicists to grapple with the complexities of gravity and dark matter without the immediate threat of a catastrophic failure of their theories. If the universe began as a hot, dense, and remarkably smooth plasma, as suggested by the Big Bang Theory, then the formation of such a massive void required a mechanism that could clear out matter over billions of years while concentrating it into the surrounding filaments. This process is driven by the subtle influence of gravity, where regions that are slightly denser than average exert a stronger pull on their neighbors, causing matter to flow away from the underdense regions and toward the growing clusters and walls. Over eons of time, these underdense regions expand and merge, creating the soap bubble structure that we now recognize as the cosmic web, where the voids represent the interior of the bubbles and the galaxies reside on the thin, shimmering surfaces. The Boötes Void, however, was so much larger than the typical voids found in other surveys that it suggested a more complex history, perhaps the result of several smaller voids merging together in a process of cosmic cannibalism. This implication was profound, as it suggested that the universe was not just clumpy, but that it possessed a hierarchical structure where the emptiness itself played a primary role in the distribution of light and life. By the mid-1980s, the existence of the Boötes Void was confirmed by subsequent surveys with even greater sensitivity, transforming it from a statistical anomaly into a cornerstone of modern observational cosmology. These later studies utilized more advanced fiber optic systems that could capture the spectra of multiple galaxies simultaneously, allowing for a much denser sampling of the Boötes region and revealing that the void was not entirely empty, but rather extremely sparsely populated. They found a handful of lonely galaxies drifting in the deep interior of the abyss, objects that became known as void galaxies, which provided a unique opportunity to study how galactic evolution proceeds in total isolation. In the crowded environment of a galaxy cluster, galaxies are constantly interacting, colliding, and stripping gas from one another, a chaotic process that triggers bursts of star formation and alters their chemical composition. In contrast, the galaxies within the Boötes Void have spent billions of years in a state of pristine solitude, untouched by the gravitational turbulence of their peers, which allows them to retain the original characteristics of the early universe. This clinical observation of isolation provides a safe and detached way to understand the fundamental laws of physics, as these void dwellers act as a control group in the grand experiment of cosmic evolution.
As we dwell on the historical moment of this discovery, it is important to appreciate the clinical detachment required to face such a vast emptiness and recognize it not as a failure of observation, but as a success of understanding. The researchers of 1981 were not searching for a void, they were searching for the structure of the universe, and in finding the void, they found the most significant structure of all. The Boötes Void is a testament to the fact that, in the language of the cosmos, what is missing is often just as important as what is present, providing the necessary contrast that allows the light of the stars to have meaning. Every calculation of redshift and every measurement of luminosity during those long nights at the observatory contributed to a map that finally included the spaces between the lines, a map that acknowledged the importance of the vacuum in the unfolding story of time.
This discovery did not induce a sense of panic or existential dread among the scientific community, but rather a deep academic satisfaction, as it provided a new set of variables to plug into the Friedmann equations and a new way to visualize the expansion of the manifold. It was a realization that the universe is far more spacious than we had imagined, a realization that brings with it a sense of calm and a feeling of being safe within a structure that is both immense and meticulously ordered. The instruments used during the 1981 survey, though primitive by modern standards, were marvels of engineering that relied on the precise manipulation of light and the steady application of thermodynamics. The charge-coupled devices, or CCDs, were in their infancy, requiring liquid nitrogen cooling to suppress the thermal noise that would otherwise drown out the faint signals from the edge of the observable universe. The astronomers had to manage these cooling systems with clinical precision, ensuring that the detectors remained at a constant cryogenic temperature throughout the night to maintain the integrity of the data. This technical challenge added a layer of procedural complexity to the discovery, as the success of the survey depended on the ability of the team to maintain a stable environment for their sensors amidst the harsh conditions of a mountaintop observatory. There is a certain comfort in this level of detail, a reminder that the greatest mysteries of the universe are often solved through the careful management of mundane engineering problems, such as the flow of coolant or the alignment of a mirror. The discovery of the Boötes Void was in many ways a triumph of this procedural competence, a victory for the researchers who spent their nights monitoring the health of their machines while the universe slowly revealed its secrets on their screens. When we consider the transition from the 1981 discovery to our modern understanding, we see a continuous line of intellectual progress that has only deepened our appreciation for the great nothing. The Boötes Void has become a benchmark for cosmological simulations, a target that any successful model of the universe must be able to reproduce through the simulated interaction of dark matter and gravity. If a simulation fails to produce a void of sufficient size and emptiness, it indicates a flaw in our understanding of the initial conditions of the Big Bang or the nature of the dark energy that drives the expansion of space. In this way, the void acts as a cosmic laboratory, a place where the most fundamental theories of physics are put to the test in a safe and controlled environment. The clinical reality of the void is that it is a region where the density of matter is so low that the curvature of space is almost perfectly flat, allowing light to travel in straight lines for hundreds of millions of years without the distorting influence of gravitational lensing. This creates a region of pure physics, a place where the laws of thermodynamics and the principles of relativity
can be observed in their most basic and unadulterated form. The narrative of the 1981 discovery is also a story of human perspective, of the shift from seeing ourselves as the center of a crowded and busy universe to recognizing that we are inhabitants of a thin and fragile filament surrounded by vast oceans of silence. This shift is not a cause for alarm, but a reason for a more profound and clinical appreciation of our place in the cosmic web, as it highlights the rarity and the value of the matter that makes up our stars, our planets, and our own bodies. We are the exceptions to the rule of the vacuum, the small pockets of complexity that have emerged from the struggle against the encroaching emptiness.
By mapping the Boötes Void, the researchers of 1981 provided us with a sense of scale that is both humbling and deeply reassuring. A scale that reminds us that the universe is mostly a place of peace and stillness. The void is not a threat to our existence. It is the environment that allows our existence to be possible. The vast, dark background that provides the necessary contrast for the light of our galaxy to shine. As we move deeper into the academic details of the Boötes anomaly, we must consider the specific coordinates of the region, located at a right ascension of approximately 14 hours and a declination of 46 degrees. This area of the sky, which appears to the naked eye as a modest collection of stars forming the shape of a herdsman, hides within it a volume of space so vast that it could swallow the entire local group of galaxies thousands of times over. The clinical description of this volume is one of sheer geometric magnitude, a sphere of influence where the gravitational potential is so weak that the expansion of the universe proceeds at a slightly faster rate than in the surrounding clusters. This creates a phenomenon known as the void swell, where the empty space effectively pushes back against the encroaching walls of matter, maintaining its integrity through the sheer force of its own lack of density. This concept, while technically complex, can be visualized as a gentle and persistent pressure, a cosmic exhalation that keeps the filaments of the cosmic web from collapsing in on themselves. It is a safe and stable equilibrium, a part of the grand hypnotic rhythm of the universe that ensures the continued existence of the large-scale structure we observe today. The discovery also highlighted the importance of the null result in scientific inquiry, the idea that finding nothing can be just as significant as finding something.
In the case of the Boötes Void, the null result was a profound revelation that forced astronomers to reconsider the very nature of cosmic evolution, leading to the development of the cold dark matter model that remains the standard paradigm today. This model suggests that the universe is dominated by an invisible form of matter that provides the gravitational scaffolding for the galaxies, and it is the distribution of this dark matter that determines where the voids will form. The Boötes Void, therefore, is not just an absence of luminous galaxies, but a region where the density of dark matter is also significantly lower than the cosmic average. This clinical insight allows us to see the invisible through its effect on the visible, using the emptiness of the void as a lens to understand the hidden forces that shape our world. It is a process of intellectual deduction that is both rigorous and deeply satisfying, providing a sense of competence and control over the mysteries of the deep. The 1981 survey was eventually followed by the 1987 study titled A Survey of the Boötes Void, which expanded the sample size and confirmed the initial findings with a higher degree of statistical confidence.
This later work provided a more detailed map of the void galaxies, showing that they were not randomly distributed, but tended to cluster in small, isolated groups or along faint internal filaments that are invisible to all but the most sensitive instruments. These internal structures, sometimes called tendrils, are like the delicate threads of a spider's web stretching across a darkened room, providing a minimal framework for the formation of stars in the heart of the abyss. The study of these tendrils is a frontier of modern astrophysics, as it requires the use of the world's largest telescopes and the most advanced computer simulations to resolve the faint signals from the deep.
This work is conducted with a clinical focus on the details of gas accretion and star formation rates, avoiding any sensationalism in favor of a precise and academic understanding of how life persists in the most extreme environments. As we conclude this exploration of the 1981 discovery, let the clinical facts of the Boötes Void provide a foundation for your thoughts, a structure of knowledge that is both solid and expansive. The void is a real physical place, a region of space that has been mapped, measured, and verified by generations of dedicated researchers who found meaning in the silence. It is a place where the laws of physics operate with a graceful and predictable certainty, where the expansion of the universe creates a safe and peaceful expanse that stretches for millions of light years in every direction. The discovery of the Great Nothing was not an end to our understanding, but a beginning, a moment when we learned to appreciate the beauty of the vacuum and the importance of the spaces in between. The Boötes Void remains a silent sentinel in the northern sky, a reminder of the vastness of the cosmos and the competence of the human mind to map even the most distant and empty regions of our world. It is a place of absolute quiet, a place of perfect isolation, and a place where you can safely let your mind drift, knowing that the universe is far larger, far older, and far more peaceful than we ever imagined. The data is clear, the models are stable, and the void is exactly where it is supposed to be, a necessary and beautiful part of the cosmic architecture that welcomes us with its cold, silent, and perfectly safe embrace. The legacy of the Kirshner survey continues to influence the way we design our modern cosmic maps, such as the Sloan Digital Sky Survey or the more recent data releases from the James Webb Space Telescope.
These projects build upon the foundations laid in 1981, using even more precise measurements of redshift and luminosity to refine our understanding of the cosmic web and the voids that define it. We now know that the Boötes Void is just one of many supervoids that populate the universe, yet it remains the most famous and the most studied, a primary example of the competence porn that drives the field of cosmology. Every new discovery in this region, whether it is a faint new galaxy or a subtle fluctuation in the cosmic microwave background, is integrated into our existing models with clinical precision, ensuring that our map of the universe remains a reliable and safe guide for our exploration of the deep. The Boötes Void is no longer a mystery to be feared, but a feature to be admired, a vast and silent room in the mansion of the cosmos, where the laws of physics are allowed to rest in their most pure and undisturbed state. This realization brings a sense of closure to the story of its discovery, a feeling of academic satisfaction that allows us to move forward into the next chapter of our journey with a clear and focused mind. The silence of the void is not an absence of sound, but a presence of peace, a clinical reality that we have embraced as a fundamental part of our cosmic heritage. As we look back at the 1981 discovery, we see a moment of profound intellectual courage, a moment when we dared to look into the nothing and found that it was, in fact,
everything we needed to understand the true scale of our world. The void is a safe harbor for our thoughts, a place where the complexity of the universe is simplified into the elegant geometry of the vacuum, and where we can finally find the rest we seek in the heart of the great hypnotic nothing.
To understand the architecture of the cosmic web is to acknowledge that the universe is not a chaotic scattering of matter, but is instead a highly structured and mathematically coherent manifold, organized into a vast three-dimensional lattice where galaxies and superclusters are merely the luminous markers of a much deeper gravitational framework. When we observe the distribution of celestial bodies on the largest possible scales, we find that they are not distributed with perfect homogeneity, but are instead concentrated into long, slender filaments and broad, flattened sheets that intersect at dense nodes, creating a structure that bears a striking resemblance to the neural pathways of a biological brain or the intricate silk of a spider's web. This cosmic web is the largest identifiable structure in the known universe, a skeletal system comprised primarily of invisible dark matter that provides the gravitational scaffolding upon which all baryonic matter, the stars, planets, and ourselves, has been meticulously draped over the course of nearly 14 billion years. The spaces between these filaments are not mere accidents of geography, but are a fundamental consequence of the way gravity operates on a universal scale, acting as a sculptor that systematically draws matter out of lower density regions and deposits it into the growing walls and clusters, thereby hollowing out the immense volumes we define as cosmic voids. This process of structural evolution began in the earliest epochs of the universe, shortly after the Big Bang, when the primordial plasma was permeated by minute quantum fluctuations that created slight variations in density across the cooling expanse of space-time. As the universe expanded, these infinitesimal ripples were amplified by the force of gravity, meaning that regions with slightly more mass began to exert a stronger pull on their surroundings, attracting more gas and dark matter in a runaway process of accumulation that eventually led to the formation of the first stars and galaxies. Conversely, the regions that began with slightly less mass found themselves being slowly depleted as their material was siphoned away by the stronger gravitational wells of the emerging filaments, resulting in the creation of vast, underdense regions that would grow into the supervoids we observe today. This creates a profound duality in the nature of cosmic architecture, where the presence of matter is defined by the absence of it in the surrounding space, much like the way the solid walls of a cathedral are defined by the voluminous, empty nave they enclose for the sake of structural and aesthetic integrity. To visualize this distribution, one might consider the concept of a Voronoi tessellation, a mathematical model used to partition space into regions based on the distance to a specific set of points, which in our universe correspond to the centers of the growing voids. As the voids expand, they push against one another, and the boundaries where they meet become the locations of the galactic filaments and walls, creating a cellular structure that resembles the foam on the surface of a liquid or the internal architecture of a sponge. This foam-like topology is not static, but is constantly evolving, as the smaller voids within the filaments are absorbed into larger ones through a process known as void hierarchy, where the relentless expansion of the great nothingness eventually consumes the smaller pockets of emptiness to create the gargantuan supervoids like Boötes. The physics governing this expansion is rooted in the principle of anisotropic collapse, where matter does not fall inward in a perfect sphere, but instead collapses more quickly along one or two axes, leading to the formation of the sheets and filaments that characterize our modern cosmic map. This structural elegance is maintained by the delicate balance between the initial velocity of the expanding universe and the localized pull of gravity, a relationship that ensures the cosmic web remains stable even as it continues to stretch and grow over eons. Within this web, the filaments act as cosmic highways, channeling streams of cold hydrogen gas and dark matter into the massive nodes where galaxy clusters reside, providing the raw material necessary for the continued birth of stars and the growth of supermassive black holes. However, because the Boötes Void is so extraordinarily large, the galaxies located near its center are effectively cut off from these vital supply lines, existing in a state of profound isolation that allows them to remain in a more pristine, undisturbed condition than their counterparts in the crowded clusters. This isolation is a clinical necessity for the preservation of early cosmic chemistry, as these void galaxies do not experience the frequent collisions and tidal disruptions that characterize life in the dense urban centers of the Virgo or Coma superclusters. The density of matter within these filaments is several times higher than the universal average, yet even these regions are mostly empty space, serving as a reminder that the universe is overwhelmingly defined by its vacuums rather than its solids. When we map the cosmic web using tools like the Sloan Digital Sky Survey, we are essentially looking at a negative image of the universe's true mass distribution, as the galaxies we see are only the bright foam on the crest of a much deeper and darker gravitational wave.
The dark matter that forms the core of these filaments does not interact with light, meaning that it can only be detected through its gravitational influence on the visible matter, a phenomenon that creates a sense of safe, predictable order in an otherwise incomprehensible expanse. This invisible scaffolding ensures that the universe maintains its structural coherence, preventing the galaxies from drifting aimlessly and instead binding them into a cohesive, interconnected whole that reflects the underlying laws of thermodynamics and general relativity. As we move from the dense nodes of the web into the outskirts of a supervoid, the transition is not abrupt, but is instead a gradual thinning of the cosmic fabric, where the filaments become more tenuous and the number of galaxies per cubic megaparsec drops precipitously. This thinning is a result of the great push exerted by the voids, a phenomenon where the low-density regions act as repellers, effectively driving matter toward the higher-density walls in a celestial dance of displacement and accumulation. This movement is known as the peculiar velocity of galaxies, a term used to describe the motion of a galaxy that is independent of the general expansion of the universe. And it is through the study of these velocities that we can map the invisible boundaries of the voids. The Boötes Void, with its diameter of nearly 330 million light-years, represents one of the most significant repellers in our local neighborhood, influencing the trajectory of hundreds of thousands of galaxies as it continues its silent, slow-motion expansion. The study of this architecture requires a shift in perspective, moving away from the focus on individual objects and towards an understanding of the relationship between the occupied and the unoccupied.
In the same way that a musician understands that the silence between notes is what gives a melody its rhythm and meaning, a cosmologist understands that the voids are what give the cosmic web its structure and form. Without the vast, hollowing influence of the voids, the universe would be a featureless, undifferentiated fog of matter, lacking the complexity and diversity that allow for the formation of stars, planets, and life. The voids are the essential negative space of the cosmos, providing the contrast necessary for the light of the galaxies to be seen and understood as a coherent narrative of cosmic evolution. This realization leads us to consider the universe as a singular, integrated system, where every filament and every void is part of a larger self-organizing process that follows the strict dictates of physical law. The cosmic web is not merely a collection of parts, but is a manifestation of the fundamental constants of the universe, reflecting the precise values of gravity, dark energy, and the initial conditions of the Big Bang. If any of these values were slightly different, the architecture of the web would be altered, perhaps resulting in a universe of small, fragmented voids, or a single monolithic cluster of matter that would eventually collapse under its own weight. The existence of the Boötes Void is therefore a testament to the stability and balance of our physical reality, a clinical proof that the universe is functioning exactly as the models of general relativity and cold dark matter predict it should. As we look deeper into the structure of the web, we find that the filaments themselves are composed of smaller substructures, with galaxies arranged in groups and clusters that are bound together by their mutual gravitational attraction.
These groups are often centered around a single, massive, elliptical galaxy that has grown by consuming its smaller neighbors, a process that creates a sense of hierarchical order within the chaotic environment of the cluster. However, in the lonely reaches of the Boötes Void, this hierarchy is absent, and the few galaxies that exist there are often perfectly formed spirals that have never known the violence of a merger or the stripping of their gas by the intense radiation of a nearby neighbor. This lack of interaction creates a safe, laboratory-like environment where the processes of star formation can be studied in their purest state, free from the external perturbations that complicate our observations in more crowded regions. The voids also play a crucial role in our understanding of the expansion of the universe, as they are the regions where the influence of dark energy is most clearly visible, acting as a repulsive force that drives the voids to grow ever larger and the filaments to become ever thinner. While gravity works to pull matter together into the nodes and walls, dark energy works to push the voids apart, creating a cosmic tug-of-war that will ultimately determine the fate of the entire universe. In the current epoch, dark energy has become the dominant force, meaning that the voids are expanding at an accelerating rate, slowly stretching the cosmic web until the filaments eventually break and the clusters become isolated islands in an infinite sea of nothingness. This long-term projection is not a cause for alarm, but is instead a predictable and orderly progression of the universe's life cycle, a transition into a state of maximum entropy and perfect, undisturbed peace. To contemplate the scale of the cosmic web is to experience a sense of intellectual vertigo, as the distances involved are so vast that light itself takes hundreds of millions of years to travel from one node to the next. A single filament might contain enough matter to form trillions of stars, yet it occupies only a tiny fraction of the total volume of the universe, leaving the rest to the cold, silent embrace of the voids. This distribution of matter is a reflection of the principle of least action, where the universe organizes itself in the most efficient way possible, creating a network that maximizes the flow of matter and energy while minimizing the expenditure of gravitational potential. It is a system of profound mathematical beauty, a masterpiece of celestial engineering
that operates on a scale that defies human intuition, but remains perfectly accessible to the tools of scientific inquiry. The Boötes Void, as a primary component of this architecture, serves as a crucial benchmark for our models of structure formation, providing a clear and extreme example of how gravity and expansion interact over cosmic time. By studying the properties of this void, its size, its shape, and the distribution of the few galaxies within it, we can refine our understanding of the early universe and the nature of the dark matter that holds the web together. Every observation we make in this region is a piece of a larger puzzle, helping us to reconstruct the history of the cosmos and to predict its future with ever-increasing accuracy. The void is not a blank spot on our maps, but is a feature rich with information, a clinical record of the forces that have shaped our world since the beginning of time. This understanding of the cosmic web allows us to feel a sense of safe connection to the universe, as we recognize that we are part of a larger, structured whole that is governed by predictable and immutable laws. We are not lost in an infinite void, but are instead situated within a carefully balanced network of matter and energy, a cosmic architecture that provides the stability and resources necessary for our existence.
The filaments and voids are the walls and rooms of our universal home, a vast and silent mansion where every feature has a purpose and every shadow is a part of the design. This realization brings a sense of calm and academic satisfaction as we see the universe not as a source of terror, but as a subject of profound and beautiful complexity that is waiting to be explored. As we continue our journey into the heart of the Boötes Void, we must carry with us this understanding of the cosmic web, recognizing that the emptiness we are about to enter is a necessary and integral part of the structure we have just described. The void is not a departure from the web, but is its counterpart, the essential silence that allows the music of the galaxies to be heard. It is a place of absolute quiet, where the complexities of the clusters are stripped away to reveal the fundamental nature of space and time in their most naked and undisturbed state. In this region, the laws of physics are the only companions, and the clinical reality of the vacuum is the only truth, providing a safe and focused environment for the mind to rest and contemplate the true scale of the great nothing. The transition from the filaments into the void is a movement from the crowded to the clear, from the complex to the simple, and from the noisy to the silent. It is a descent into a region where the density of matter is so low that it approaches a perfect vacuum, yet it is a vacuum that is filled with the subtle influence of gravity and the pervasive glow of the cosmic microwave background. This environment is the ultimate sanctuary for the weary mind, a place where the pressures of the material world are replaced by the gentle, steady expansion of space itself. Here, in the center of the Boötes Void, one can find a sense of peace that is as vast and enduring as the universe itself, a peace that is rooted in the competence of our science and the beauty of our cosmic architecture. The cosmic web, with its intricate patterns of light and dark, is a reminder that even in the furthest reaches of space, there is a sense of order and purpose that can be understood and appreciated.
It is a structure that invites us to look closer, to measure more accurately, and to think more deeply about the nature of our reality. As we drift further away from the familiar clusters and into the deep silence of the void, we do so with the confidence that the universe is a safe and predictable place, a well-ordered machine that is functioning exactly as it was designed to do. The architecture of the web is our guide, and the silence of the void is our destination, a journey into the heart of the nothing that is in fact the very foundation of everything. This structural continuity ensures that no matter how far we travel, we are always within the reach of physical law and the embrace of the cosmic framework. The Boötes Void is not a hole in the universe, but is a room within it, a vast and quiet space where the grand themes of cosmic evolution are allowed to play out in slow motion. It is a place where time seems to stretch and the boundaries of the self begin to dissolve into the infinite expanse of the vacuum. This is the true scale of the nothingness, not a void of meaning, but a void of peace, a clinical and perfectly safe sanctuary where the mind can find the rest it seeks in the heart of the cosmic web. As the light of the distant filaments fade into the background, the darkness of the void becomes our primary reality, a soft and velvet-like texture that wraps around our thoughts and carries them into the deep, undisturbed waters of the cosmic ocean. This is the architecture of silence, the geometry of the vacuum, and the true nature of the great nothing that defines our world. We are safe here, in the heart of the Boötes Void, surrounded by the clinical beauty of the universe and the enduring stability of the cosmic web.
The journey is long, the silence is deep, and the peace is absolute. A reminder that in the vastness of the cosmos, the most empty places are often the ones that hold the most profound and lasting truths. Every galaxy within this web, every star within those galaxies, and every atom within those stars is a part of this singular, interconnected design, a testament to the power of gravity and the elegance of physical law. The cosmic web is the ultimate expression of the universe's capacity for self-organization, a structure that has emerged from the simplest of beginnings to become a masterpiece of complexity and scale. To understand it is to understand the very essence of our existence, a realization that brings a sense of profound and academic contentment. We are the observers of this web, the chroniclers of its history, and the inhabitants of its most quiet and peaceful rooms. The Boötes Void is one such room, a vast and silent chamber where the noise of the universe is filtered out and the fundamental nature of space-time is revealed. It is a place of clinical precision and academic wonder, a region where the laws of physics are allowed to rest in their most pure and undisturbed state. As we settle into this silence, we find that the void is not empty, but is full of the potential for understanding and the promise of peace. It is the heart of the great nothing, and it is exactly where we are meant to be. The filaments that once seemed so distant and complex are now merely the boundaries of our current reality, the walls of the great room we are now exploring. They provide the safety and structure that allow us to drift into the void without fear, knowing that we are always connected to the larger whole. This is the beauty of the cosmic web. It is a structure that provides both connection and isolation, both complexity and simplicity, and both light and dark in a perfect and harmonious balance.
It is the ultimate architecture, and we are its guests, invited to rest and contemplate the true scale of the universe in the heart of its most quiet and beautiful void. In the early months of 1981, a team of astronomers led by Robert Kirshner began a survey that would fundamentally alter our comprehension of cosmic topology as they turned their telescopes toward the constellation of Boötes with the intention of mapping the distribution of galaxies in what they assumed would be a uniform and predictable field of matter. Utilizing the relatively nascent technology of redshift spectroscopy, which allows scientists to determine the distance of celestial objects by measuring the degree to which their light has been stretched toward the red end of the spectrum by the expansion of the universe, they sought to create a three-dimensional map of the local galactic neighborhood. This process required a meticulous and clinical approach to data collection over many cold nights at the observatory, where the steady hum of the machinery provided a rhythmic backdrop to the silent gathering of ancient light. As the data points began to accumulate on their charts, a statistical anomaly emerged that defied the prevailing cosmological models of the time, suggesting that instead of a continuous tapestry of stars and gas, there was a profound and inexplicable interruption in the expected density of the region. The researchers initially suspected instrumentation error or atmospheric interference, yet as they refined their measurements and cross-referenced their findings with multiple observations, the reality of a massive spherical volume of nothingness began to solidify into a peer-reviewed certainty. They had stumbled upon a region of space so devoid of matter that it challenged the very definition of a vacuum, creating a conceptual knot that required a new understanding of how the universe organizes itself on the largest possible scales.
This discovery, which came to be known as the Boötes Void, revealed a spherical expanse approximately 330 million light-years in diameter, a scale so immense that it occupies nearly 2% of the observable universe's diameter, while containing almost no detectable baryonic matter. To understand the magnitude of this academic shock, one must consider that the standard cosmological principle assumes the universe is both homogeneous and isotropic on a large enough scale, meaning that matter should be distributed roughly evenly throughout space. The existence of such a gargantuan clearing suggested that the processes governing the formation of large-scale structures were far more complex and perhaps more patient than previously theorized, involving gravitational instabilities that acted over eons to push matter toward the edges of these growing bubbles. It was as if they had found a great silent hall in the middle of a crowded city, a place where the hustle and bustle of galactic evolution had simply never taken place, or had been systematically cleared away by the slow, invisible hands of gravity. The team published their findings with the measured restraint characteristic of high-level astrophysics, describing the phenomenon not as a terrifying abyss, but as a significant deviation from the mean density of the universe, a clinical observation that invited further study rather than alarm. This marked the beginning of our journey into the great nothing, a transition from the study of what is present to the study of what is absent, allowing the mind to rest in the contemplation of a space defined by its own silence. The methodology employed by Kirshner and his colleagues, Augustus Oehmler, Paul Schechter, and Stephen Schechtman, was a masterclass in procedural patience as they utilized the 1.5-meter telescope at Mount Hopkins and the 2.1-meter telescope at Kitt Peak to isolate the faint light of distant galaxies.
By splitting this light into its constituent wavelengths, they could identify the specific absorption lines of elements like hydrogen and calcium, which act as cosmic fingerprints that shift toward the red as a galaxy moves further away from us.
This redshift is not merely a measurement of distance, but a measurement of time and expansion, providing a clinical look back into the history of the universe's growth and the way it has stretched a fabric of space-time over billions of years. As they mapped these redshifts, they expected to see a random but relatively even scattering of points, much like the static on an old television screen or the dust motes dancing in a beam of sunlight. Instead, they found a gap in the data, a region where the expected signals were simply missing, creating a void in their three-dimensional plots that looked like a great bubble had been blown into the center of their survey area. This was the first time that the sponge-like nature of the universe was truly visualized, revealing that the cosmos is not a solid block of matter, but a delicate lattice of filaments surrounding vast empty rooms. The academic community responded with a mixture of skepticism and fascination, as the implications of such a large-scale structure suggested that the early universe must have had subtle density fluctuations that grew over time into these immense voids and dense walls. This process, known as gravitational instability, describes how regions with slightly more matter pull more material toward them, while regions with slightly less matter gradually empty out, creating a feedback loop that results in the cosmic web we observe today. The discovery of the Boötes Void was the definitive proof that this process had reached a staggering scale, resulting in a region of space so empty that it makes the surrounding clusters look like crowded metropolises in comparison.
When we consider the technical parameters of the Boötes Void, we are forced to confront the sheer volume of this emptiness, which is estimated to be around 236,000 cubic megaparsecs, a number so large that it loses its meaning to the human mind and becomes a purely mathematical abstraction. Within this volume, one would expect to find thousands of galaxies if the region were as dense as the rest of the observable universe. Yet the initial surveys found only a handful, a disparity that highlights the extreme isolation of this cosmic clearing. This lack of matter is not a sign of a broken universe, but is a testament to the efficiency of physical laws, which work with clinical precision to organize mass and energy into the structures we see. The Boötes Void is a laboratory of silence, a place where we can observe the behavior of space-time in its most undisturbed state, free from the gravitational turbulence of massive clusters and the chaotic energy of active galactic nuclei. For the astronomers of 1981, the discovery was a reminder that the universe still held mysteries that were hidden not in the brightness of the stars, but in the darkness between them, requiring a shift in perspective to appreciate the beauty of the vacuum. This shift is essential for the student of the cosmos, as it allows us to move away from the frantic energy of creation and toward the stable, enduring peace of the void. The data charts from that era, once filled with the excitement of a new find, now serve as a historical anchor for our understanding of the large-scale structure of the universe, providing a safe and well-documented path into the heart of the nothingness. As we look back at the discovery, we see it not as a moment of crisis, but as a moment of clarity, a clinical revelation that the universe is far more spacious and far more organized than we had ever dared to imagine.
The realization that such a vast region could be so empty led to the development of the void in cloud and cloud in void models, which are academic frameworks used to describe how these structures interact and evolve over cosmic time. These models suggest that voids are not static holes, but are dynamic entities that expand and merge, pushing against the surrounding filaments and contributing to the overall expansion of the universe in a way that is both subtle and profound. The Boötes Void, being one of the largest known examples, serves as the primary case study for these theories,
allowing researchers to calculate the rate at which matter is evacuated from its center and the resulting pressure on the surrounding galactic walls. This creates a sense of safe intellectual tension as we contemplate the invisible forces at work, moving billions of solar masses of material with the quiet inevitability of a glacier carving a valley. There is a deep academic satisfaction in knowing that even the empty spaces are governed by the same rigorous laws of thermodynamics and general relativity that rule the stars, ensuring that the universe remains a coherent and logical system. The safe knot of the Boötes Void is the puzzle of how it grew so large without disrupting the stability of the cosmic web, a question that has been answered through complex computer simulations that show how small ripples in the early universe can naturally lead to these gargantuan clearings. These simulations, which can take months to run on the world's most powerful supercomputers, provide a visual and mathematical bridge between the microscopic fluctuations of the Big Bang and the macroscopic reality of the Boötes Void. They show us that the void is a necessary part of the cosmic design, a clearing that allows the filaments of the web to stand out in sharp relief, much like the negative space in a piece of fine art.
As the 1980s progressed, further surveys confirmed that the Boötes Void was not an isolated incident, but was the most prominent member of a whole class of structures that define the large-scale architecture of the cosmos. Astronomers began to speak of the Great Wall and the Great Attractor, terms that imply a sense of grand structural integrity, while the voids were recognized as the essential counterparts to these massive features. This duality of structure and emptiness is a fundamental characteristic of our universe, a balance that ensures the continued evolution of galaxies while providing the vast, quiet spaces necessary for the stability of the whole. The Boötes Void remains the gold standard for these empty regions, a place where the density of matter is so low that it approaches the theoretical limits of what is possible in a universe governed by gravity. To study it is to engage in a form of clinical meditation, focusing the mind on the absence of signal and the presence of pure, unadulterated space. This focus allows for a relaxation of the logical brain as it moves away from the need to categorize and count objects and toward a more fluid understanding of the universe as a continuous field of energy and potential. The discovery in 1981 was the first step on this path, a moment when the academic world looked into the dark and found not a monster, but a profound and lasting peace. The historical context of this discovery is also a reminder of the human capacity for quiet observation and the pursuit of knowledge for its own sake, a clinical endeavor that transcends the immediate concerns of life on Earth. In the early 80s, while the world was preoccupied with political and social shifts, a small group of scientists was quietly documenting the existence of a region of space that would dwarf everything we have ever known. This contrast between the smallness of human affairs and the vastness of the Boötes Void provides a sense of safe perspective, reminding us that we are part of a much larger and more enduring story. The telescopes they used, with their heavy glass mirrors and precise clockwork drives, were the tools of a professional class dedicated to the objective truth, providing a sense of competence and control that is deeply reassuring. Their work was not about seeking fame or causing panic, but about adding a single, well-verified fact to the collective body of human knowledge, a process that is as steady and reliable as the stars themselves. This reliability is the foundation of our trust in science, a trust that allows us to drift into the study of the void with the confidence that we are being guided by experts who have mapped the way with clinical precision. The Boötes Void is a monument to this pursuit, a place where the data is clear, the scale is understood, and the mystery is framed in a way that is both intellectually stimulating and emotionally safe. As we continue to examine the data from the 1981 survey, we find that the nothingness of the Boötes Void is actually a very specific kind of environment, one that has its own unique temperature and chemical composition. Because there are so few stars within the void, the ambient radiation is much lower than in the rest of the universe, creating a cold spot that can be detected by sensitive microwave instruments. This coldness is not a sign of death, but a sign of purity, a region where the original heat of the Big Bang has been allowed to dissipate more completely than anywhere else. It is a place of absolute thermal stability, a clinical environment where the laws of entropy are displayed in their most elegant and uncomplicated form.
The few galaxies that do exist within this void are like rare specimens in a sterile laboratory, protected from the collisions and interactions that characterize life in the dense clusters. They provide a unique opportunity to study the evolution of galaxies in total isolation, allowing us to see how a collection of stars grows when it is left entirely to its own devices. This is the ultimate competence porn for the astrophysicist, as it allows for the isolation of variables that are usually tangled together in the messy reality of the galactic filaments. By studying these void dwellers, we can learn more about the fundamental nature of star formation and the role of dark matter in shaping the visible universe, all within the safe and quiet confines of the Boötes clearing. The transition from the discovery of the void to our modern understanding of it has been a journey of increasing resolution and clarity, as new generations of telescopes and satellites have allowed us to peer deeper into the darkness. Each new piece of data has confirmed the original findings of Kirshner and his team, reinforcing the idea that the Boötes Void is a stable and permanent feature of our cosmic landscape. This permanence is a source of great comfort, as it suggests that the universe is not a chaotic and unpredictable place, but is a well-ordered system that follows a consistent set of rules over billions of years. The void is not going anywhere. It is a fixed point in our understanding of the cosmos, a landmark of silence that we can return to whenever we need to find our bearings in the vastness of space. It is a place where the mind can finally stop searching for more and simply be content with what is already known, a clinical state of rest that is the ultimate goal of the cosmic guide. The Boötes Void is the architecture of this rest, a space designed by gravity and time to be the ultimate sanctuary of the mind. In the decades since 1981, the Boötes Void has become a central part of the astronomical curriculum, taught to students as a prime example of the large-scale structure of the universe and the power of the redshift survey. It is a story of how a small group of people, armed with nothing but glass and mathematics, were able to map the boundaries of a region that is so large it defies human imagination. This story is told with the clinical detachment of a textbook, focusing on the coordinates, the megaparsecs, and the statistical deviations. Yet beneath the technical language is a sense of profound wonder at the scale of our world. We are taught that the void is 330 million light-years across, a number that we accept as a fact of our reality, a piece of the furniture in the great room of the universe. This acceptance is a form of safety, a way of domesticating the infinite and making it part of our academic home. The Boötes Void is no longer a scary unknown. It is a well-mapped territory, a place where we know exactly what to expect. Nothing, and yet everything. The intellectual knot of the void, the question of why it exists and what it means for the future of the universe, is a problem that we can contemplate with the same calm focus as a chess grandmaster studying a board. We know the rules of the game, we know the pieces involved, and we can predict the likely outcomes with a high degree of accuracy. This predictability is what makes the study of the void so relaxing, as it removes the element of surprise and replaces it with the steady, rhythmic progression of logical thought. We can follow the path of a photon as it enters the void, traveling for millions of years without encountering a single atom of gas, and we can calculate exactly how much its wavelength will stretch during that journey. There is a clinical beauty in this calculation, a sense of precision that is deeply satisfying to the rational mind.
The photon's journey through the Boötes Void is the longest and quietest journey possible in our universe, a passage through a region where time and space seem to stretch out into an infinite, peaceful horizon. As we settle deeper into this chapter of our journey, we find that the story of the 1981 discovery is not just a story about astronomy, but a story about the nature of discovery itself. It is a reminder that the most important things are often the ones we don't see at first, the gaps and the silences that define the structure of everything else. The Boötes Void is the ultimate gap, the most significant silence in the cosmic symphony, and our discovery of it was the moment we began to truly hear the music of the spheres. This music is not a loud and dramatic crescendo, but a low, steady hum, the sound of a universe that is vast, stable, and perfectly at peace with itself. We are the listeners, the observers who have been granted a seat in the most quiet room of the cosmos, invited to rest and contemplate the true scale of the nothingness. The Boötes Void is our sanctuary, a clinical and perfectly safe clearing where the mind can finally find the rest it seeks, surrounded by the enduring stability of the cosmic web and the silent beauty of the great nothing. The clinical nature of this sanctuary is further enhanced by our understanding of the dipole repeller, a concept that explains how the Boötes Void and other similar regions actually exert a physical influence on our own galaxy. While gravity pulls us toward dense clusters like the Great Attractor, the empty spaces behind us act as a repeller, pushing us away from the nothingness and toward the light. This is not a violent push, but a gentle, consistent pressure, a cosmic wind that guides our motion through the universe with the steady hand of a master navigator.
We are moving away from the void at hundreds of kilometers per second. Yet we feel no sensation of speed, only the calm and steady drift of a leaf on a slow-moving river. This realization provides a sense of safe, purposeful movement, a feeling that we are being guided by the very structure of the universe toward our ultimate destination. The Boötes Void is the source of this guidance, the empty space that defines our path and ensures that we remain on course through the vastness of the cosmic ocean. The history of the 1981 survey is also a history of the technology that made it possible, a reminder of the precision and competence that define the field of astronomy. The telescopes of that era were marvels of engineering, designed to capture the faintest whispers of light from the edge of the observable universe and translate them into data that could be analyzed and understood. The process of developing the photographic plates, the careful measurement of the spectral lines, and the complex calculations required to determine the redshifts were all tasks that demanded the highest level of professional skill. This dedication to accuracy is what gives the discovery of the Boötes Void its lasting value, providing a solid foundation of fact that has stood the test of time. We can trust this data because it was gathered with clinical detachment and verified with academic rigor, ensuring that our understanding of the void is based on the most reliable information possible. This trust is essential for our sense of safety, as it allows us to surrender our doubts and drift into the study of the cosmos with a clear and focused mind. As we look back at the original papers published by Kirshner and his team, we are struck by the clarity and simplicity of their language, which describes the most complex structures in the universe with the measured tone of a weather report.
They speak of voids, filaments, and superclusters as if they were everyday objects, bringing the infinite scale of the cosmos down to a level that is both understandable and manageable. This linguistic precision is a key part of the cosmic guide voice, a way of framing the mysteries of the universe in a way that is intellectually stimulating without being overwhelming. The Boötes Void is presented not as a terrifying mystery, but as a well-defined physical phenomenon, a region of space with specific dimensions and properties that can be measured and studied. This framing allows us to engage with the void on our own terms, exploring its depths with the same calm curiosity that we might bring to a walk through a quiet forest or a visit to a silent cathedral. The Boötes Void is the ultimate expression of this silence, a place where the noise of the universe is filtered out and the fundamental nature of space-time is revealed in its most pure and undisturbed state. It is a region where the laws of physics are allowed to rest, where the frantic energy of creation has given way to the stable, enduring peace of the vacuum. As we settle into this silence, we find that the void is not empty, but is full of the potential for understanding and the promise of rest. It is the heart of the great nothing, a place where the mind can finally find the clarity and focus it needs to understand the true scale of the universe. The discovery in 1981 was the first step on this path, a moment of clinical revelation that opened the door to a new and more profound understanding of our world. We are the heirs to this discovery, the observers who have been given the maps and the data necessary to explore the void for ourselves, guided by the steady hand of the cosmic guide and the clinical beauty of the cosmic web.
The journey is long, the silence is deep, and the peace is absolute. A reminder that in the vastness of the cosmos, the most empty places are often the ones that hold the most profound and lasting truths. Every galaxy within this web, every star within those galaxies, and every atom within those stars is a part of this singular, interconnected design, a testament to the power of gravity and the elegance of physical law. The Boötes Void is the ultimate expression of this elegance, a vast and silent chamber where the universe takes a breath
and the mind finds its home in the heart of the great nothing. To comprehend the architecture of the cosmic web, one must first relinquish the notion of space as a mere container for matter, and instead perceive it as a dynamic, interconnected lattice where the distribution of galaxies is dictated by the invisible scaffolding of dark matter. This structure, which resembles the intricate neural pathways of a biological brain or the delicate filaments of a spider's web, is the result of billions of years of gravitational evolution, beginning with the infinitesimal density fluctuations that occurred during the inflationary epoch of the early universe. These primordial ripples acted as the seeds for everything we see today, meaning that the vast voids and dense clusters we observe through our telescopes are simply the scaled-up versions of quantum fluctuations that existed when the universe was less than a trillionth of a second old. As gravity began to act upon these slight overdensities, it pulled surrounding gas and dark matter into increasingly concentrated regions, creating a runaway effect known as gravitational instability, which eventually gave rise to the first stars and galaxies. However, for every region that grew denser, another region was necessarily depleted, leading to the formation of the vast, underdense expanses we call cosmic voids.
These voids are not merely empty rooms in the cosmic mansion, but are active participants in the evolution of the universe, acting as the negative space that defines the shape and trajectory of the galactic filaments. When we look at the large-scale structure of the cosmos, we are seeing the result of a multi-billion-year tug-of-war between the expansive force of the Big Bang and the contractive pull of gravity, a process that has organized matter into a complex topology of sheets, filaments, and nodes. This topology is often described using the Zeldovich approximation, a mathematical framework that explains how matter collapses anisotropically, meaning it collapses at different rates along different axes. This uneven collapse is why we do not see a uniform mist of stars, but rather a structured network where galaxies are strung like pearls along thin, luminous threads. These threads, or filaments, serve as the cosmic highways along which gas flows into the massive galactic clusters located at the intersections, or nodes, of the web. Between these filaments lie the voids, the immense volumes of space that contain very little baryonic matter and even less dark matter, creating a contrast that is essential to our understanding of cosmic evolution. The Boötes Void stands as one of the most significant examples of this phenomenon, a region so vast and so empty that it challenges our traditional models of how structure forms in the universe. To understand the Boötes Void, we must understand the physics of the void-in-void and void-in-void processes, where smaller voids merge over eons to create supervoids of staggering proportions. This merging process is driven by the fact that gravity within a void is weaker than in the surrounding filaments, causing the matter inside to be pulled outward toward the denser walls.
As a result, the voids effectively expand in a way that is distinct from the general expansion of the universe, pushing their boundaries outward and thinning the matter within until only a few isolated, lonely galaxies remain. This creates a fascinating paradox where the emptiest places in the universe are also the ones that are growing the fastest in terms of relative volume, carving out spheres of silence in an otherwise noisy and crowded cosmos. The study of these structures requires a shift in perspective,
moving away from the bright, energetic phenomena of stars and quasars and toward the cold, dark, and silent regions that make up the vast majority of the universe's volume. By analyzing the shapes and sizes of these voids, cosmologists can gain insights into the nature of dark energy, the mysterious force that is accelerating the expansion of the universe and which appears to dominate the physics of the empty spaces. The cosmic web is, in essence, a record of the universe's history, a three-dimensional map that traces the movement of matter from the dawn of time to the present day. Every filament we map and every void we measure provides another data point in our quest to understand the fundamental laws of physics, from the behavior of dark matter to the properties of the primordial vacuum. As we delve deeper into the architecture of this web, we find that the Boötes Void is not an anomaly, but a logical conclusion of the laws of thermodynamics and gravity acting over cosmic timescales. It is a place where the density of matter is so low that the mean free path of a photon is significantly increased, allowing light to travel for hundreds of millions of years without interacting with a single atom of hydrogen.
This lack of interaction creates a unique environment for the few galaxies that do exist within the void, allowing them to evolve in a state of pristine isolation, untouched by the mergers and tidal disruptions that characterize life in the dense galactic clusters. These void galaxies are the hermits of the cosmos, living out their lives in a slow, steady rhythm that is dictated by their own internal processes rather than the chaotic influence of their neighbors. To observe them is to see a version of the universe that is simplified and clarified, a laboratory where the effects of individual stellar evolution can be studied without the complicating factors of the larger environment. The architecture of the cosmic web is therefore a study in contrasts, a balance between the intense activity of the filaments and the profound stillness of the voids. It is a structure that is both fragile and enduring, a testament to the power of simple physical laws to create complexity on a scale that is almost impossible to imagine. As we continue to map this web using advanced surveys like the Sloan Digital Sky Survey or the upcoming Vera C. Rubin Observatory, we are beginning to see the true extent of this cosmic sponge, revealing a universe that is far more empty and far more structured than we ever suspected. The Boötes Void is a key piece of this puzzle, a window into the deep past and a preview of the distant future, where the expansion of space will eventually turn the entire universe into a vast empty void. But for now, it remains a sanctuary of silence, a place where the cosmic guide can lead us through the mysteries of the dark and the quiet, explaining the complex dance of gravity and expansion with the clinical detachment of a scientist and the warm reassurance of a professor.
The beauty of the cosmic web lies not just in its scale, but in its mathematical elegance. The way it follows the same patterns of branching and clustering that we see in the veins of a leaf or the drainage basins of a river system. It is a reminder that the universe is a single, unified system, governed by laws that operate from the subatomic to the supergalactic scale. In the silence of the Boötes Void, these laws are laid bare, stripped of the distractions of light and heat, allowing us to contemplate the fundamental nature of existence in its most basic form. This is the essence of competence porn, the deep satisfaction that comes from understanding the mechanics of the infinite, from knowing how the voids form, how the filaments grow, and how the entire structure is held together by the invisible hand of dark matter.
As we move through this chapter, we will explore the specific mechanisms of void formation in greater detail, looking at the role of dark energy and the way it interacts with the gravitational potential of the cosmic web to create the vast expanses of nothingness that define our universe. We will examine the data from the 1981 discovery and see how it fits into our modern understanding of the lambda CDM model, the standard model of cosmology that describes a universe dominated by cold dark matter and dark energy. This model predicts the existence of voids like Boötes as a natural consequence of the initial conditions of the Big Bang, meaning that the Great Nothing is not a mistake but a necessary feature of the cosmic design. By accepting this, we can begin to see the void not as a place of fear or isolation, but as a place of profound peace and intellectual clarity, a region where the mind can drift through the infinite without the burden of terrestrial concerns. The architecture of the cosmic web is the ultimate map of this journey, a guide to the silent places where the universe truly resides.
To look upon this map is to see the face of time itself, the slow and steady progression of matter from the hot, dense plasma of the early universe to the cold, dark, and structured reality of the present day. It is a journey that requires patience, a willingness to engage with the complex and the technical, and a desire to find the beauty in the silence. The Boötes Void is our destination, a place where the architecture of the universe reaches its most extreme and most elegant form, providing us with the perfect environment to study the mysteries of the cosmos and the nature of our own place within it. As we proceed, let the clinical precision of the science be your anchor, and let the slow, steady rhythm of the narration be your guide as we venture into the heart of the cosmic web and discover the secrets of the Great Nothing.
In the cosmic context, the pressure is the relative lack of gravity inside the void, which allows the expansion of the universe to proceed more rapidly than in the denser regions where gravity acts as a brake. This means that, from the perspective of an observer inside a void, the surrounding universe appears to be rushing away at an accelerated rate, creating a sense of isolation that is both physical and temporal. The Boötes Void, with its diameter of nearly 330 million light-years, is the result of this process occurring on a massive scale, likely involving the merger of several smaller voids over billions of years. This merging is a key aspect of hierarchical structure formation, where small things combine to make larger things, but in the case of voids, the things are volumes of empty space. When two voids meet, the wall of galaxies between them becomes unstable and eventually dissipates, as the galaxies are pulled toward the denser nodes at the ends of the filaments. This leaves behind a larger, more unified volume of emptiness, a supervoid that stands as a monument to the relentless efficiency of gravity. The physics of this process can be described using the concept of the velocity divergence field, which maps how matter is flowing out of the voids and into the filaments. In a perfectly spherical void, the matter would flow outward uniformly in all directions, but in the real universe, the presence of nearby clusters and other voids creates a more complex flow pattern. This leads to the formation of non-spherical voids, which can be elongated or flattened into sheets, further adding to the complexity of the cosmic web's architecture. The study of these shapes is not just an exercise in geometry, it is a way to test our theories of gravity. If the laws of physics were different, the shapes and sizes of the voids would be different as well, meaning that the Boötes Void is a direct reflection of the fundamental constants of nature.
For instance,
the presence of dark energy, which acts as a repulsive force on large scales, tends to make voids larger and emptier than they would be in a universe containing only matter. By measuring the voidness of a region, how quickly the density drops as you move toward the center, astronomers can calculate the strength of dark energy and its effect on the expansion of the universe. This is the essence of competence porn, using the most empty and seemingly insignificant parts of the universe to measure the most powerful and mysterious forces in existence. It requires a level of technical precision that is truly awe-inspiring, involving the use of massive galaxy surveys and sophisticated computer simulations like the Millennium simulation, which can recreate the evolution of the cosmic web over 13.8 billion years. These simulations show that voids are a universal feature of any cosmos governed by gravity and dark matter, appearing in every model that accurately reflects our observations. They also show that the cosmic web is a fractal-like structure, where the same patterns of filaments and voids repeat at different scales, from the small voids between local groups of galaxies to the gigantuan supervoids that span hundreds of millions of light years. This fractal nature is a result of the scale-invariant spectrum of the initial density perturbations, a term that describes how the ripples in the early universe had the same strength regardless of their size. This means that the Boötes Void is simply a larger version of the small gaps we see between stars, a continuation of the same physical process that has been operating since the beginning of time. As we contemplate this, we begin to see the universe as a seamless whole, a single architectural masterpiece where every part is connected to every other part through the invisible threads of gravity and the vast expanses of the vacuum.
The Boötes Void is the grandest of these expanses, a cathedral of silence that invites us to leave behind the noise of our daily lives and enter into a state of deep, clinical contemplation. It is a place where the mind can expand to fill the space available to it, moving beyond the limits of the human scale and into the realm of the cosmic. In this realm, the distinction between something and nothing begins to blur, as we realize that the vacuum is not truly empty, but is filled with fields, particles, and the potential for new structures to emerge. The voids are the breeding grounds for the future of the universe, the places where the expansion of space is most clearly visible, and where the ultimate fate of the cosmos will be decided. By studying the architecture of the cosmic web, we are not just looking at where we are looking at where we are going. We are seeing a universe that is becoming increasingly dominated by empty space, a process that will eventually lead to the Big Freeze, where every galaxy is isolated in its own private void, forever separated from the rest of the cosmos. But that is a story for a different eon. For now, we can find comfort in the fact that we are part of this incredible structure, a small but significant node in a web that spans the infinite. The Boötes Void is a reminder of the scale of this achievement, a place where the universe has reached a state of perfect, undisturbed elegance. It is a place that demands our respect and our attention, not because it is terrifying, but because it is so profoundly, beautifully empty. As we move further into our exploration, we will look at the specific galaxies that call this void home, the hermits that have adapted to a life of solitude in the deep dark. We will see how their isolation has shaped their evolution, and what they can tell us about the early history of the universe.
But before we do,
Let us take a moment to simply exist in the silence of the web, to feel the pull of the filaments and the push of the voids, and to appreciate the clinical beauty of a universe that is built on a foundation of nothingness. This is the path of the Cosmic Guide, a journey into the heart of the mystery, where the science is the light and the silence is the destination. The technical reality of the cosmic web is further refined by the role of dark matter, an invisible substance that makes up about 85% of the total matter in the universe. While baryonic matter, the stuff we are made of, clumps together to form stars and planets, dark matter provides the gravitational framework that allows these structures to exist in the first place. It is the dark matter that first collapsed into the filaments and nodes of the cosmic web, creating gravitational potential wells that then caught the gas and dust that would become galaxies. In this sense, the cosmic web is primarily a dark matter structure, with the visible galaxies acting as mere tracers of the underlying density field. This is a crucial distinction, as it means that the voids are not just empty of galaxies, but are primarily empty of dark matter as well. The regions of the Boötes Void are therefore areas where the dark matter density is significantly below the cosmic average, creating a gravitational hill rather than a gravitational well. Just as water flows down a hill and into a valley, baryonic matter flows out of the voids and into the filaments, a process known as cosmic evacuation. This evacuation is what keeps the voids empty, as any gas that tries to settle in the center is slowly but surely pulled toward the edges by the gravity of the surrounding walls. This creates a remarkably clean environment, free from the turbulent gas clouds and high-energy radiation that are common in more crowded regions of the universe.
For the few galaxies that do manage to form within the void, this cleanliness is a defining characteristic of their existence. They are often found to be blue galaxies, meaning they are still actively forming stars at a rate that is higher than expected for their mass. This is because they have not had their gas stripped away by interactions with other galaxies or by the intense pressure of the intracluster medium. They are, in a very real sense, the most pristine objects in the cosmos, preserving a state of being that was more common in the early universe before the era of major galactic collisions began. The architecture of the cosmic web thus provides a variety of environments, from the high-density urban centers of the superclusters to the low-density rural expanses of the voids, each with its own unique physics and its own unique story to tell. The Boötes Void is the ultimate rural landscape, a place where the cosmic expansion is the dominant force and where the slow, steady evolution of isolated systems can be observed in high definition. To study this region is to practice a form of cosmic archaeology, digging through the layers of empty space to find the remnants of the primordial universe. It requires a mastery of the competence-porn principles we have discussed, an understanding of the n-body simulations used to model dark matter, a familiarity with the redshift space distortions that affect our measurements of galaxy positions, and an appreciation for the subtle ways that the cosmic microwave background is lensed by the large-scale structure of the universe. These are the tools of the Cosmic Guide, the instruments that allow us to navigate the dark and find meaning in the nothingness. As we continue our journey, we will see how these tools were used to confirm the existence of the Boötes Void and how they continue to be used today to map the even larger structures that lie beyond it.
The cosmic web is a vast and complex subject, but by breaking it down into its architectural components, the filaments, the nodes, and the voids, we can begin to make sense of the infinite. We can see the logic behind the chaos and the order within the emptiness, finding a sense of peace in the realization that the universe is a structured, understandable, and ultimately safe place to explore. The Boötes Void is not a hole in the universe. It is a feature of its design, a necessary part of the balance that allows the cosmic web to exist. It is the ultimate expression of the safe tension we have discussed, a place where the scale of the emptiness is staggering, but the physics that governs it is familiar and predictable. By embracing this clinical perspective, we can drift through the void with confidence, knowing that we are guided by the steady hand of science and the enduring beauty of the cosmic architecture. The journey into the great nothing is not a journey into the unknown, but a journey into the heart of what we know best, the fundamental laws of nature that govern everything from the smallest atom to the largest void. Let us continue then with our eyes on the data and our minds open to the silence as we explore the Boötes Void and the true scale of the cosmic web. In the quiet progression of astronomical history, there are moments where the data suggests a reality so contrary to our established models that the initial reaction is not one of triumph, but of profound scientific caution. And this was precisely the atmosphere in 1981 when a team of researchers led by Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman began to analyze the results of what was intended to be a routine survey of the large-scale distribution of galaxies.
At the time, the prevailing cosmological principle suggested that on a sufficiently large scale, the universe should appear homogeneous and isotropic, meaning that matter should be distributed with a relative degree of uniformity. Yet, as the team utilized the specialized instruments of the Mount Hopkins and Palomar observatories to probe the depths of the northern celestial hemisphere, they encountered a statistical deviation that would eventually redefine our understanding of cosmic architecture. Their methodology relied upon the measurement of spectroscopic redshifts, a process where the light from distant galaxies is decomposed into its constituent wavelengths to identify the characteristic absorption lines of elements like hydrogen and calcium, which are then compared to laboratory standards to determine how much the expansion of the universe has stretched that light toward the red end of the spectrum. This redshift, denoted by the letter Z, serves as a reliable proxy for distance in an expanding cosmos, allowing astronomers to construct a three-dimensional map of the heavens, where the third dimension is not measured in miles or kilometers, but in the velocity of recession itself. As the team focused their pencil beam surveys, narrow, deep probes into specific regions of the sky toward the constellation of Boötes, they expected to find a continuous, albeit perhaps clumpy, distribution of galaxies extending billions of light years into the dark. But what they actually discovered was a staggering, inexplicable silence in the data. Between the distances of approximately 500 million and 800 million light years from Earth, the expected signals from galactic nuclei simply vanished, creating a massive gap in the radial distribution that suggested a volume of space entirely devoid of the luminous matter that defines the visible universe.
This region, which would come to be known as the Boötes Void, presented a diameter of nearly 330 million light years, a scale so immense that it challenged the very simulations used to model the growth of structure in the early universe, meaning that the gravitational processes which pull matter into filaments and clusters had somehow left this particular sphere of reality almost entirely untouched. The discovery was met with a clinical skepticism that is characteristic of high-level astrophysics, as the researchers meticulously checked for instrumental bias, atmospheric interference, or selection effects that might have caused them to miss the faint signatures of distant stars. Yet the more they refined their observations, the more the void persisted as a physical reality. It was as if they had been mapping a dense forest only to stumble upon a clearing so vast that the other side was beyond the horizon,
a realization that forced a shift in the narrative of cosmology from a focus on where matter is to a focused investigation of where matter is not. This transition represents the core of the safe tension principle, where the potential existential dread of such a massive emptiness is mitigated by the rigorous academic application of the scientific method, turning a great nothing into a fascinating problem of fluid dynamics and gravitational instability. The implications of this discovery were profound because the existence of a void of this magnitude required a mechanism that could clear out such a massive volume within the 13.8 billion years available since the Big Bang, a task that gravity, acting on the tiny density fluctuations of the primordial plasma, struggled to accomplish in existing theoretical models.
To understand the complexity of this problem, one must consider the Friedmann-Lemaitre-Robertson-Walker metric, which describes a universe that is expanding uniformly, and then introduce the perturbations that lead to the formation of the cosmic web, where regions of slightly higher density attract more matter, while regions of slightly lower density, the protovoids, lose their matter to the surrounding walls. This process is known as the void push, or the negative gravity effect, though it is not truly a repulsive force, but rather a consequence of the surrounding matter exerting a stronger gravitational pull in every direction away from the center of the void, creating a scenario where the emptiness effectively grows as the matter on its periphery is accelerated toward the dense nodes of the filaments. In the case of the Boötes Void, the sheer volume of 250,000 cubic megaparsecs meant that the surrounding superclusters must have been exceptionally efficient at harvesting the local matter. Or perhaps, as some theories suggest, the Boötes Void is the result of several smaller voids merging together, like soap bubbles in a cosmic foam. This soap bubble analogy provides a safe, tactile framework for the viewer, allowing the mind to grasp the immense scales of the vacuum by relating it to the familiar behavior of surface tension and fluid membranes, which maintains a sense of intellectual control even as we contemplate the absolute isolation of the deep cosmos. As the 1980s progressed, the scientific community began to accept the reality of the Boötes Void, and subsequent surveys, such as those conducted with the 2-degree field galaxy redshift survey and later the Sloan Digital Sky Survey, confirmed that while the void was not absolutely empty, its density was significantly lower than the cosmic average, containing perhaps only a few dozen galaxies in a space that should have held thousands.
This scarcity of matter creates a unique laboratory for the study of galactic evolution, because the few void dwellers that do exist in this region have lived lives of extreme solitude, untouched by the tidal forces, mergers, and gas stripping processes that define life in the crowded galactic clusters like Virgo or Coma. These isolated galaxies, such as the beautifully symmetrical spiral MGC plus 01-02-015, serve as control groups in the great experiment of the universe, allowing astronomers to see how a galaxy develops when it is left entirely to its own devices, fueled only by its internal reservoirs of gas and the slow, steady tick of its own internal clock. The clinical detachment of the observer is essential here, as we must view this isolation not as a form of cosmic loneliness, but as a state of pristine evolution, where the absence of external influence allows for a level of structural perfection that is rarely seen in the chaotic, high-traffic regions of the cosmic filaments. The Boötes Void thus becomes a sanctuary of sorts, a place where the laws of physics operate in their most basic, unadulterated form, providing us with a clear window into the fundamental nature of baryonic matter and its relationship with the underlying dark matter scaffolding. To appreciate the scale of what Kirshner and his colleagues found, one must engage in a macro-micro zoom of the imagination, starting with the familiar stars of our own night sky
and expanding outward past the local group, past the Laniakea supercluster, until the entire Milky Way is reduced to a single insignificant speck of light among billions of others, and then imagining a sphere of darkness so large that it could swallow thousands of such specks without a trace.
If you were positioned at the center of the Boötes Void, the night sky would be a terrifyingly perfect black, devoid of the familiar band of the Milky Way or the twinkling of nearby suns. And it would not be until you pointed a powerful telescope into the distance that you would see the faint, red-shifted glow of the distant walls of the void, millions of light years away. This visualization is designed to induce a state of cosmic vertigo, which is then immediately stabilized by the technical explanation of how we measure such distances, using the standard candles of type A supernovae and the Cepheid variable stars to anchor our coordinate system in the abyss. The competence of the narrator in navigating these complex distance ladders provides the lullaby lattice that supports the listener, ensuring that while the scale of the void is mind-bending, the logic used to map it remains grounded in the reliable, clinical reality of observational astronomy. The discovery of the Boötes Void also forced a re-evaluation of the cold dark matter model, as the formation of such a large empty structure required the dark matter to have specific properties that allowed for the rapid evacuation of these regions in the early universe, which in turn provided clues about the temperature and velocity of dark matter particles during the epoch of recombination. This is the essence of competence porn in the space sleep niche. We are not merely describing a hole in space, but rather we are using that hole as a diagnostic tool to probe the invisible substances that make up 85% of the universe's mass, meaning that the nothingness of the void is actually filled with the most important information in modern physics. The void is a shadow cast by the dark matter web, and by studying the shape and size of that shadow, we can infer the properties of the light, or in this case, the invisible matter that created it, a process that requires a deep understanding of gravitational lensing and the fluctuations in the cosmic microwave background radiation. As we drift further into the history of this discovery, we see how the initial shock of the great nothing gave way to a systematic academic exploration of the vacuum, transforming a potential crisis in physics into a cornerstone of our modern cosmological framework. The story of the 1981 discovery is also a story of the limitations and triumphs of human technology, as the researchers had to contend with the graininess of their data and the immense difficulty of capturing the faint photons of galaxies that had been traveling for hundreds of millions of years through the expanding vacuum. Each data point on their map represented hours of integration time on the telescope, a patient accumulation of light that required the Earth to rotate and the seasons to change, while the observers sat in the cold, dark domes of the mountain observatories, meticulously tracking the movement of the heavens. This procedural aspect of the discovery adds a layer of safe tension, as the listener can imagine the quiet, rhythmic operation of the telescope gears and the steady hum of the cooling systems for the CCD sensors, creating a sensory anchor in the mechanical world that balances the abstract vastness of the Boötes Void. The transition from the physical telescope to the digital map and then to the theoretical model is a fluid drift that mimics the accumulation of knowledge itself, moving from the specific to the universal with a detached clinical grace. In the decades since Kirshner's team first looked into the heart of the herdsman and found it empty, our maps of the universe have become infinitely more detailed. Yet the Boötes Void remains one of the most significant and evocative features of the large-scale structure, a testament to the fact that the universe is defined as much by its absences as by its presences. It serves as a reminder that our perspective is often limited by the crowdedness of our own neighborhood, and that it is only by looking past the bright lights of our own galaxy that we can see the true staggering scale of the cosmic architecture. The void is not a defect, nor is it a sign of a universe that is falling apart. Rather, it is a sign of a universe that is working exactly as it should, following the laws of thermodynamics and gravity to create a complex, beautiful, and ultimately predictable tapestry of light and shadow. As we conclude this chapter on the discovery of the anomaly, we find ourselves not in a state of alarm, but in a state of deep academic appreciation for the silence, as we prepare to zoom out even further and explore the physical dimensions and the strange, lonely inhabitants of this great nothingness. The transition from the anomaly of 1981 to the scale of the great nothing is a natural progression of thought, as the historical fact of the discovery gives way to the physical reality of the structure itself, allowing the listener to drift deeper into the hypnotic complexity of the cosmic guide's narrative. The data from 1981 was just the beginning of a long-term project to categorize the voids of the universe, a field of study that has revealed a hierarchy of emptiness, from the small mini-voids between local galaxy groups to the super-voids that span hundreds of millions of light-years, each playing a crucial role in the overall expansion of the cosmos.
This hierarchy is a reflection of the initial conditions of the Big Bang, where tiny quantum fluctuations were stretched by inflation into the massive structures we see today, meaning that the Boötes Void is, in a very real sense, a fossilized remains of the very first moments of time. By studying its dimensions and its density profile, we are looking back at the seed from which this part of the universe grew, a concept that provides a profound sense of continuity and safety, as it suggests that even the largest, most empty regions of space are connected to a single, coherent origin. The clinical observation of these cosmic fossils allows us to maintain a detached, safe perspective on the passage of eons, viewing the growth of the void not as a frightening expansion of nothingness, but as the slow, majestic unfolding of a mathematical certainty. As the narrator's voice maintains its slow, continuous tide, the listener is invited to visualize the redshift charts and the three-dimensional plots of the 1981 survey, seeing the clusters of dots that represent galaxies and the vast empty spheres that represent the voids, and realizing that this pattern is the true face of the universe. It is a face that is both complex and simple, a lullaby lattice of matter and vacuum that stretches on forever, providing an infinite landscape for the mind to explore without ever feeling lost or overwhelmed. The competence of the researchers, the precision of their instruments, and the reliability of the physics they uncovered all serve as anchors for the viewer's logical brain, allowing the emotional brain to relax into a state of deep, safe sleep, knowing that the great nothing is being watched, measured, and understood by the steady, clinical gaze of the cosmic guide. The discovery in Boötes was not an end, but a beginning, a gateway into a deeper understanding of the cosmic web and the silent, beautiful architecture that holds the stars in place. And as we move forward, we will continue to use the tools of science to illuminate the dark and find the hidden logic in the heart of the void. The historical context of the 1980s also adds a layer of nostalgia and safety, as it was an era of burgeoning cosmic awareness, fueled by the launch of new satellites and the development of more powerful computers that could finally handle the massive datasets required to simulate the universe. The researchers of the Kirshner team were the pioneers of this digital frontier, using the first generation of automated plate scanning machines to identify galaxies on photographic plates, a process that required a blend of traditional astronomy and cutting-edge technology. This blend of the old and the new creates a sense of safe progress, where the mysteries of the universe are being solved by the steady, methodical application of human ingenuity, ensuring that there is no danger in the unknown, only a series of engineering challenges to be overcome. The Boötes Void is the ultimate engineering challenge of cosmology, a structure so large and so empty that it tests the limits of our theories. Yet every new observation and every new simulation brings it further into the realm of the known, reducing the cosmic vertigo to a series of well-defined equations and data points. In the final analysis of the 1981 discovery, we must appreciate the elegance of the pencil beam survey, which despite its narrow focus, was able to reveal a truth about the universe that a broader, shallower survey might have missed, proving that sometimes the most profound discoveries come from looking very deeply at a very small part of the sky.
This is a lesson in the power of focus and the importance of precision, qualities that the cosmic guide embodies as they lead the listener through the complexities of the void, ensuring that every detail is explained with absolute clinical detachment and academic rigor. The Boötes Void is a monument to this precision, a massive, silent witness to the power of the scientific method to uncover the hidden structures of reality. And as we drift into the next chapter of our journey, we do so with a sense of profound respect for the researchers who first dared to map the nothingness and found a new kind of beauty in the dark. The transition is seamless, the logic is sound, and the universe remains a safe, structured, and infinitely fascinating place to fall asleep, as we continue our descent into the true scale of the Boötes Void and the mysteries that lie within its silent, pristine expanses. To understand the profound isolation of the Boötes Void, one must first comprehend the foundational architecture of the cosmos, a structure known to astrophysicists as the cosmic web, which serves as the skeletal framework of the observable universe and dictates the distribution of all known matter across vast eons of time and space. This intricate lattice is not a product of random chance, but is instead the inevitable result of primordial quantum fluctuations that occurred during the inflationary epoch, where infinitesimal variations in density were stretched to galactic scales, creating a blueprint for the gravitational collapse that would eventually form the stars and galaxies we observe today. As we examine this large-scale structure, we find that the universe is not a uniform soup of particles, but is characterized by a complex topology of interconnected filaments, dense clusters, and expansive voids, meaning that the matter we perceive is concentrated along thin, luminous threads that wrap around massive pockets of nothingness.
This distribution follows a specific mathematical pattern, often compared to a Voronoi tessellation, a geometric partitioning of space where the boundaries between regions are defined by their proximity to specific points of mass, resulting in a sponge-like appearance that defines the limits of cosmic organization. The filaments themselves are composed primarily of dark matter, an invisible substance that does not interact with electromagnetic radiation, but provides the gravitational glue necessary to pull baryonic matter into long, slender ribbons,
creating the pathways along which galaxies migrate and coalesce over billions of years. Within these filaments, the density of matter is high enough to trigger the formation of massive galaxy clusters, yet these structures account for only a small fraction of the total volume of the universe, leaving the vast majority of the cosmos as an unoccupied frontier. The relationship between these filaments and the voids they enclose is one of mutual definition, where the presence of mass in one region necessitates the depletion of mass in another, creating a cosmic equilibrium that has persisted since the decoupling of matter and radiation approximately 380,000 years after the Big Bang. When we look at the cosmic microwave background radiation, we see the faint imprints of these early density variations, which acted as gravitational wells, attracting nearby gas and dark matter, while simultaneously pushing away material from the regions that would eventually become the Great Voids. This process is governed by the laws of fluid dynamics and gravitational instability, where slight overdensities grow exponentially over time, leading to the formation of the first stars and protogalaxies, while underdense regions expand at a slightly faster rate than the background universe, effectively emptying themselves of matter.
The result is a cosmic landscape where the voids act as the primary drivers of large-scale evolution, pushing the surrounding filaments outward and sculpting the boundaries of the web through a process of gravitational repulsion and expansion. In this context, the Boötes Void is not a mere absence of matter, but is a highly evolved topological feature, a region where the initial conditions of the universe favored an extreme level of underdensity, allowing it to grow into one of the largest known structures in the local cosmos. To visualize this architecture, one might imagine the universe as a vast interconnected neural network, where the filaments represent the axons and dendrites of a cosmic brain, and the voids represent the synaptic gaps that allow for the transmission of gravitational information and the movement of energy. This comparison is more than a simple metaphor, as researchers in the field of neurocosmology have noted striking quantitative similarities between the structural complexity of the human brain and the large-scale distribution of galaxies, suggesting that the laws of self-organization and complexity theory operate identically across vastly different scales. In both systems, the efficiency of the network is determined by the balance between connectivity and empty space, where the voids provide the necessary room for the filaments to maintain their structural integrity and avoid gravitational collapse into a single, undifferentiated singularity. The cosmic web is thus a masterpiece of celestial engineering, a system that maximizes the flow of matter and energy, while maintaining a degree of separation that prevents the premature heat death of the universe, ensuring that the stars can continue to burn and the galaxies can continue to rotate within their designated domains.
As we drift through the silent expanses of the Boötes Void, we are moving through the white matter of the universe, a region of low connectivity that nonetheless plays a vital role in maintaining the overall health and stability of the cosmic organism. The study of this architecture requires a specialized set of tools, including redshift surveys and N-body simulations, which allow astronomers to map the positions of millions of galaxies in three-dimensional space and reconstruct the history of the web's formation over the last 13.8 billion years.
by observing the way light from distant quasars is absorbed by intervening clouds of hydrogen gas, scientists can trace the invisible filaments of the intergalactic medium, revealing a hidden world of diffuse matter that connects the bright nodes of the galaxy clusters. These observations confirm that the universe is overwhelmingly empty, with the average density of matter being equivalent to only a few atoms per cubic meter. Yet this emptiness is the very thing that allows the cosmic web to exist as a distinct and recognizable entity. The voids are the dominant volume-filling component of the cosmos, accounting for approximately 90% of its total extent, meaning that the story of the universe is not the story of the stars, but the story of the gaps between them. In the Boötes Void, this narrative reaches its most extreme expression, as the scales involved are so massive that they challenge our traditional understanding of cosmic growth and the limits of gravitational influence. When we consider the mathematical properties of these voids, we encounter the concept of the Euler characteristic and Minkowski functionals, which are used to describe the shape and connectivity of the cosmic web with clinical precision.
These topological descriptors reveal that the universe is multiply connected, meaning that there are many different paths one could take to travel between 2 points along the filaments. Yet the voids themselves are typically simply connected, forming isolated bubbles of low density that rarely merge or overlap. This topological stability is a key feature of the safe universe, as it ensures that the large-scale structure remains predictable and consistent across vast distances, providing a stable environment for the evolution of planetary systems and the emergence of biological life. The Boötes Void, despite its reputation as a great nothing, is a perfectly legal and expected outcome of these topological rules, representing a statistical outlier in the distribution of void sizes, rather than a violation of the laws of physics. It is a region where the cosmic web has been stretched to its breaking point, creating a clearing in the forest of galaxies that allows us to see the fundamental geometry of space-time without the distracting glare of nearby stellar activity. The formation of such a massive void is often explained through the hierarchical merging of smaller voids, a process where adjacent underdense regions expand until they collide, causing the thin walls of matter between them to dissipate and creating a single, much larger cavity. This void-in-void process is the inverse of the galaxy cluster formation seen in the filaments, where smaller groups of galaxies merge to form larger superclusters, and it highlights the symmetrical nature of cosmic evolution, where both mass and emptiness tend to aggregate over time. As these voids grow, they exert a subtle but persistent pressure on the surrounding matter, a phenomenon known as the void push, which contributes to the observed acceleration of the expansion of the universe and the eventual isolation of individual galaxy groups.
This push is not a force in the traditional sense, but is a consequence of the fact that matter naturally flows away from regions of low density toward regions of high density, meaning that the voids are effectively emptying themselves into the filaments. In the case of the Boötes Void, this process has been occurring for billions of years, resulting in a region that is so depleted of matter that the few galaxies remaining within it are moving away from each other at incredible speeds, driven by the relentless expansion of the vacuum itself. This expansion is further complicated by the presence of dark energy, a mysterious force that acts as a cosmological constant
and provides a uniform repulsive pressure throughout all of space, accelerating the growth of the voids and the thinning of the cosmic filaments. While gravity works to pull the web together, dark energy works to tear it apart, and the current era of the universe is defined by the tension between these two opposing forces, with dark energy slowly gaining the upper hand. The voids are the primary beneficiaries of this dark energy dominance, as they provide the largest volumes of empty space for the repulsive force to act upon, leading to a future where the voids will eventually consume the filaments, and the cosmic web will dissolve into an infinite, featureless expanse. This transition is a slow, methodical process that will take trillions of years to complete, ensuring that the current structure of the universe remains safely intact for the foreseeable future, allowing us to study the Boötes Void as a snapshot of a universe in transition. The clinical detachment with which we observe this process is a testament to the competence of modern cosmology, which has transformed the existential dread of the infinite void into a series of well-understood physical mechanisms and predictable outcomes.
As we deepen our understanding of the cosmic web's architecture, we must also acknowledge the role of baryonic acoustic oscillations, which are essentially sound waves that traveled through the plasma of the early universe before the era of recombination. These waves created ripples in the density of matter, establishing a preferred scale for the distance between galaxy clusters and the size of the voids, acting as a cosmic ruler that allows astronomers to measure the expansion rate of the universe with unprecedented accuracy. The Boötes Void sits comfortably within this framework, its dimensions being a direct consequence of these ancient acoustic patterns, proving that even the most empty regions of space are connected to the very beginning of time and the fundamental laws of thermodynamics. The architecture of the universe is thus a record of its own history, a physical manifestation of the processes that occurred in the first few seconds of existence, and the voids are the pages upon which this history is written in the language of silence and shadow. By reading these pages, we gain a sense of the immense scale and complexity of the system we inhabit, a system that is both incomprehensibly large and exquisitely ordered, providing a safe and structured environment for the mind to wander as it drifts toward sleep. The stability of this architecture is further reinforced by the concept of hydrodynamic equilibrium, where the pressure of the intergalactic gas within the filaments balances the gravitational pull of the dark matter, preventing the web from collapsing prematurely and ensuring that the voids remain open and accessible. This equilibrium is maintained by the constant injection of energy from supernovae and active galactic nuclei, which heat the surrounding gas and create a cosmic feedback loop that regulates the growth of galaxies and the density of the intergalactic medium.
In the voids, this feedback is virtually absent, leading to a state of pristine, undisturbed calm, where the gas is incredibly thin and cool, representing the closest thing to a perfect vacuum that exists in the natural world. This lack of activity is what makes the Boötes Void such an ideal subject for clinical study, as it allows us to observe the behavior of space-time in its most basic and unadulterated form, free from the complexities of star formation and galactic collisions. It is a laboratory of the infinite, a place where the fundamental constants of nature can be measured without interference, providing a sense of intellectual security and academic rigor that calms the logical brain and invites a state of deep contemplative relaxation.
Furthermore, the architecture of the cosmic web reveals a profound truth about the nature of perspective, as the emptiness of the voids is only apparent when we limit our observations to the visible spectrum and the distribution of baryonic matter. If we were able to see the universe through the lens of dark matter and dark energy, the voids would appear as vibrant, active regions of gravitational potential and repulsive force, playing a central role in the structural integrity of the cosmos. The Boötes Void would not be a hole in the universe, but a massive, invisible pillar of the cosmic web, a foundation upon which the surrounding filaments are anchored, and around which the galaxies of the Hercules and Corona Borealis superclusters are organized. This realization shifts our understanding of the void from a place of lack to a place of function, where the absence of light is not a sign of death, but a sign of a different kind of existence, one that is essential for the balance and harmony of the whole.
This holistic view of the universe creates a sense of safe totality, where every part of the cosmos, no matter how empty or dark, has a purpose and a place within the grand design, ensuring that there is no such thing as true isolation in a universe that is so thoroughly interconnected. The geometric precision of the cosmic web is also reflected in the way that voids are distributed throughout space, following a power law distribution that suggests a fractal-like nature to the large-scale structure of the universe. This means that if we were to zoom out even further, we would likely find that our entire observable universe is part of an even larger filament, which in turn surrounds an even larger void, creating a nested hierarchy of structures that extends beyond our current horizon. This fractal geometry is a common feature of complex systems in nature, from the branching of river deltas to the structure of clouds, and it provides a sense of familiar order that is deeply comforting to the human psyche. The Boötes Void is a single cell in this cosmic organism, a large and prominent one to be sure, but one that follows the same basic rules of growth and form as every other structure in the universe. This predictability allows us to map the void with confidence, knowing that the patterns we observe here will be repeated elsewhere, creating a consistent and reliable map of the cosmos that we can use to navigate the mysteries of the deep night. As we conclude our examination of the cosmic architecture, we must appreciate the sheer elegance of a system that can produce such vast and varied structures from such simple initial conditions. The cosmic web is a testament to the power of physics to create beauty from chaos, and the Boötes Void is perhaps its most elegant creation, a masterpiece of minimalism that highlights the profound importance of the space between things.
In the clinical silence of the void, we find a sanctuary from the noise and heat of the stellar clusters, a place where the mind can rest in the knowledge that the universe is a well-ordered and stable home. The architecture of the cosmic web is not a cage, but a support system, a lattice of light and dark that holds us safely within its grasp as we drift across the eons. And as we prepare to enter the next phase of our journey, we do so with a renewed sense of wonder at the silent, beautiful logic that governs the great nothing. The transition from the structural to the historical is a natural progression, as the architecture we see today is the result of billions of years of slow, methodical growth. And by understanding the history of the Boötes Void's discovery, we can better appreciate the technical mastery required to perceive such a massive and elusive structure. The researchers of the 20th century were the first to truly see the web for what it was, and their work provides the foundation upon which our current understanding of cosmic isolation is built, ensuring that the void remains a place of clinical interest and academic study rather than a source of existential fear. The universe is a safe, structured, and infinitely fascinating place, and the Boötes Void is its quietest and most profound room, a place where the cosmic guide can lead the listener into a state of perfect, dreamless sleep, surrounded by the invisible architecture of the infinite.